As mentioned in the last video, I'm going to cover the usage of three-valued logic to model modal logic and explain why three-valued logic fails at modeling modal logic. Let us go back to close to a century ago when Polish philosopher Lukasiewicz mentioned that when you talk about future propositions, when you talk about future events, they are neither true nor false. We cannot fit them into classical logic because when we try to do so, you cannot assign a definite true value to a future statement because the truth value will be indeterminate at the present. Therefore, his question is, how can we formalize this kind of natural language statements into logic? And his proposal was to come up with a third truth value. So there's true and false in a binary system. That's why it's called a binary system, because it can be represented by either 0 or 1, 0 corresponding to false and 1 corresponding to true. But in a three-value system, as Lukasiewicz originally proposed, you have a third logic value called uncertainty, uncertain, which can be abbreviated as a U, and now your logic system is called ternary because there are three possible truth values. You can represent them arithmetically by a few different systems. Usually in binary logic, we use the Boolean system 0 or 1. But then in ternary logic, you have got more freedom to represent things. You may see either one of these four being used in texts or in research papers, or you can even have other ways of representing ternary logic. But for this video, we are going to adopt the balanced ternary system, which is the most common and the easiest to manipulate arithmetically because it is symmetric. Now let us talk about output patterns in order to contrast Boolean logic and ternary logic. So let the arity of the logic, which is given by the constant k, as in a k-array logic, the k, the arity, refers to the number of different true values. Binary logic has an arity of 2 because it has true and false as truth values, and as such, ternary logic has an arity of 3. A k-array logic has 2 to the power of k output patterns. This can be seen, this is illustrated in this diagram that I made. An output pattern essentially refers to a map from one truth value to the other. For example, one of the output pattern, as shown here, is an arrow, is a unidirectional arrow from T to F. This output pattern converts all T's to F's. It converts T to F. That's one output pattern. The second output pattern is F to T. The third output pattern is F to F. And the fourth output pattern is T to T. So Boolean logic has 4 output patterns. Using this same strategy for ternary logic, we have got T to U, U to T, U to F, F to U, T to F, F to T, T to T, U to U, and F to F. So there are 9 output patterns. And mathematically, we can put it as 2 to the power of k, because you're essentially picking pairs of different pairs of k amount of truth values, and they are distinct pairs. Now let us move on to binary operators. What exactly are binary operators? Binary operators, as shown here on this diagram, are basically truth table. One binary operator corresponds to one truth table. An example of a binary operator is AND. Another example is OR. Another example is XOR, which is the exclusive OR. NOT is not a binary operator. What binary operators do is that they take two different true values from two different propositions or two different variables, and then it maps it to a specific truth value. For example, AND is a binary operator in which it takes a Cartesian product of the truth value of P and Q. It takes a pair of truth values, and depending on the nature of the pair of truth values, it maps it to an output truth value. For example, if your pair of truth values P and Q is true and true, then the AND binary operator will map it to an output of true. If it is false and true, then the AND binary operator will map it to an output of false. So this is how a binary operator works. Boolean logic has 16 distinct binary operators, which means you can come up with 16 distinct binary operators, 16 distinct truth tables for Boolean logic when you take two propositions and you form an output. For ternary logic, when you take two propositions and you map it to an output, you will form close to 20,000 different distinct truth tables. This is the huge increase in complexity. It is more than exponential in nature, right? It is a huge increase. And how do we get this formula? For a k-array logic, the number of distinct binary operators is actually given by k to the power of k squared. Let us look at the truth table on the left side. T1, T2, T3, T4 all the way to Tk are the different truth values of a k-array logic. In a k-array logic, the arity will be equal to the number of distinct truth values. In binary logic, you got an arity of 2, therefore there are two distinct truth values. When you set up a truth table, on the side of P and Q, you are essentially forming permutations of pairs of truth values, distinct pairs of truth value. So the number of permutations is given by k to the power of k. K to the power of k, sorry, not k to the power of k, k to the power of number of rows. K to the power of the number of rows refers to the number of possible outputs. And when you take k multiplied by k, which is k squared, k to the power of k. K multiplied by k squared, you are finding the number of pairs of P and Q. So when you perform your permutation, you will get k to the power of number of rows, which is k to the power of k squared. Let us now move on to the truth tables of three-valued logic. This is the same for all systems of three-valued logic, or rather most systems that are predominant in modern logic. When you perform the negation, the only main difference from this is the addition of a u truth value. It behaves quite logically. U means that you don't know the truth value, because that's what it's been defined for by Lukasiewicz. So when you don't know whether something is true or false, and you say not A, you won't know the negation either. So it explains this. For the rest, you can perform it in an iterative manner. Let's take an example here. For example, for n to be true, both a and b must be true. If b is false and a is unknown, both a and b can no longer be true. Therefore, it's false. However, if b is true and a is unknown, a can be either true or false. If a is true, then a and b is true because b is true. However, if a is false, then a and b will be false. The thing is, a is unknown. Therefore, you will not know whether a and b is true or false. And as such, a and b will be unknown. This is an example of it. You can repeat this process to deduce the truth tables for the inclusive OR and exclusive OR. Let's move to a more interesting part of three-valued logic. This can be applied for binary logic, but it is more useful in three-valued logic and higher-ordered n-valued logic. Essentially, if we represent truth values by integers, -1, 0, and 1, we are basically performing arithmetic on the balanced ternary system of three-valued logic. We interpret the truth values as true integers, and we can perform algebraic manipulations on variables. So over here, a and b corresponds to the truth value of a, and b corresponds to the truth value of b. When we make a statement p or q, a corresponds to the truth value of p, and b corresponds to the truth value of q. When we say p or q, we are essentially taking the maximum of the truth values of p and q. This can be proven by comparing the truth tables of the disjunction and of this function here. On the other hand, when we say p and q, it is given by the minima of the truth values of p and of q. And the maxima can actually be simplified into an algebraic equation, into a polynomial. A and b are either -1, 0, or 1. If you plug this into a calculator, you key in the truth values of a and b, you will get the answer, you will get a numerical value that corresponds to the truth value of p or q. How do we prove this arithmetic representation? We first notice that for any integer a and any integer b, the sum of a and b is equal to the maximum of a and b plus the minimum of a and b. Because the maximum of a and b, if the maximum of a and b is a, then the minimum of a and b is b. So it will be a plus b. And vice versa, no matter what a and b are. And therefore this explains this statement, which we will call E1. And for all integers a and b, the distance between a and b, which must have an absolute, because you don't know whether a is the larger one or b is the larger one. So to account for the fact that distance is always positive, you absolute the difference. The distance between a and b is the maxima of a and b minus the minimum of a and b. Essentially, you can think of it as the distance between two numbers is equal to the value of the larger number minus the value of the smaller number. We will name this equation E2. and we actually come up with a system of simultaneous equation. We can solve this by using algebra. We can use the method of elimination. We take half of E1 minus E2. We are going to get the max AB will cancel each other out, and when we take half of 2 min AB, you will get minimal of AB. And when you simplify the equation, you'll get half of A plus B minus the absolute of A minus B. From the definition of modulus, we can expand the modulus sign out to make it a principal square root of A minus B squared. Principal square root refers to taking only the positive part of the square root, which is what a modulus does. If you square it and then you take the positive root, you are essentially converting all negative numbers into its positive forms, and all positive forms will remain as positive because a negative number squared will be positive. You get these two equations. But how do you remove the square root and get back to this? Well, I can't think of a way to do it. These two equations are in literature. You can find these two equations. It's more of an elementary algebraic thing. You can prove, in fact, that these two equations at the bottom is equivalent to these two equations at the top, simply by showing all cases of A and B, since they can only take the values -1, 0, or 1. I don't think there is any other better ways. This simplification only works for the values -1, 0, and 1. For any other values, this simplification won't work, and you may need to have a square root in your solution. So that's the interesting part for three-valued logic. It is that you can actually simplify disjunction and conjunctions by a polynomial equation. An exercise that for the reader is to derive the polynomial equation for the statement P exclusive or Q, which means either P or Q. And I will show the solution here. Ignore the final equal sign. This is actually the most simplified solution, I guess. If you expand it, it will become an extremely long polynomial. But the brief steps to do so is by definition of exclusive OR. This is the definition in classical binary logic, and you first have to notice that this definition also carries forward in three-valued logic. The truth tables for this matches the truth tables for exclusive OR that we showed previously, and you can show this by writing it out. It's quite an elementary fact. We use the definition of AND and OR. We apply it twice to simplify them into min and max functions, and then we use our previous simplifications of the min and max functions. We substitute the polynomials in, and you will form this long equation. If you input this equation into Wolfram alpha or anything, and you replace A and B with the true values of A and B, you will get the corresponding answer that corresponds to the true values of P exclusive or Q. So this is the solution. Very long, very tedious. There's no point expanding it. It's just a waste of time, but it's an interesting, I guess, mathematical outcome. Now let us move on to material conditional. Material conditional is always more of a secondary definition of logical operations because it's more complicated, and usually it's related very much to its more basic logical operations like conjunction, disjunction, negation, and so on. Now we're actually going to make the distinction between two main classes of three-valued logic. There's the clean logic and there's the Lukasiewicz logic. The main difference between these two logics is simply in how they define the material conditional. For clean logic, the material conditional is shown in the left-hand side, where the material conditional is equivalent to to this function, or not A, B, not A or B. Similar, in fact, is similar to classical logic. It's a direct mapping, it's a direct translation of binary classical logic to ternary logic, and U implies U will be unknown in clean logic. But then in Lukasiewicz logic, he mirrored what clean logic did, but he changed the result for U implies U to be true. There's a more intuitive explanation to this. If I say if A then B, and A and B are both unknown, then A implies B should be true, because an unknown fact should imply an unknown fact. So Lukasiewicz logic is a more intuitive characterization of the implication, logical operation. However, it doesn't directly fit into a translation of binary logic as opposed to clean logic, because they took it and they changed, they edited the truth value of one single entry, one single output, and that's the main difference. From now on, we are going to stick to Lukasiewicz logic. However, I will account for the fact that clean logic is a thing, and I will try to factor it in my further proofs and show that the outcomes of the conclusions and the theorems after this hold, no matter if you take clean logic or Lukasiewicz logic as your definition for the material conditional. Now we're going to look at the Tarski-Lukasiewicz mapping. Lukasiewicz introduced a one-place connective. He used the diamond and the square to represent possibility and necessity. This is pretty much a thing in modal logic tradition. And he defined diamond and the box modal operators using three-valued logic with the truth table as provided. This can be thought of in an intuitive way by considering the postulate that P is possible if and only if P is not false. You know, when I say that it is possible that Singapore is in Europe, it implies, or rather is equivalent to saying that the statement Singapore is in Europe is not false, because this statement may be true or unknown. We do not know about its truth value. That's why we say it's possible. It's possible. I don't know whether it's true. I can't confirm. It's just a possibility. And this can be put in on a more formal note by this truth table. For necessity, if you think of the statement, it is necessary that 2 plus 2 equals to 4. This implies that 2 plus 2 equals to 4 is true. Alright? It is not unknown. If it's unknown, I can't say it's a necessary fact. I must know for certain that it is true. Therefore, it cannot be false and it cannot be unknown. And it explains this truth table. When I say necessary that P is only true if and only if P is true. Now let us do an exercise using Lukasiewicz logic. It also works for clean logic, but let's use Lukasiewicz logic for now. Show that this statement is a tautology. P is necessary is equivalent to saying that it is not possible that it is not P. This is also a tautology in modal logic, in fact, and it is one of the equivalences, one of the most basic equivalences of modal logic. Maybe you can pause this video for a while over here and try it. If not, I will move on to the solution. This is my way of representing truth tables. Basically, when I have the variable, in this case it's only P, I permutate all possible true values of the variable. P can be T or F or U, and then I put the whole statement down, necessary that P is equivalent to saying that it is not possible that it is not P. And for each symbol, I will first copy the truth values, the given true values for P here. TFU, I'll copy it. P is TFU and P is TFU. And then for every symbol to the left of P or to the right of P, depending on the order of logical operation, I will apply the symbol onto P and derive the result. For example, over here, P is TFU. When I move to the left hand side, because necessary is a logical operation that precedes the right hand side operation, necessary that P, TFU becomes TFF, because P is necessary if and only if it is true that P, and therefore I get this column. And then for the other P, I always start with the variable of the proposition. P is TFU, I say not P. I move to the left, not P. I negate everything, I get FTU. And then I move on. For this branch, I can pause it for now because I can further elaborate on this branch. If you can see, the biconditional actually splits the statement into two separate branches. I'm simply evaluating the branches and then comparing them. This branch is already settled. The left hand branch is TFF. The right hand branch, we move left one more step. We get, is it possible that it is not P? Well, I apply possible to FTU, I get FTT. As long as it is true or unknown, it will be possible. And then I apply another not. I apply another negation to the possibility. So is it not the case that it is possible that it is not P? I apply the negation to FTT, I'll get TFF. So these are my branches. TFF is my right branch result, and TFF is my left branch result. Because the left branch and the right branch results are equal, it means that the equivalence operator is fulfilled, and therefore for all cases TF and U, the biconditional will be TTT. Because it is true for all cases, the biconditional is a tautology, therefore it's proven. Let us move on to the more salient issue of why Tarski and Lukasiewicz failed. Why is it that after their extensive effort in characterizing modal logic with three-valued logic, no one after them is using three-valued logic to define modal logic? Or why is it that this field has stopped and we in fact moved on to other methods at characterizing modal logic? There are multiple reasons for that. It's a whole slew of disadvantages that render the Tarski-Lukasiewicz system inferior as compared to many other systems that had existed at that time. For example, Lewis systems, Lemon systems, and even the Brouwer-Hating Kolmogorov system. The first interesting fact about any three-valued logic is that the law of the excluded middle does not hold. In fact, the law of the excluded middle is false. It's no longer the case that P or not P. Why? Because P or not P assumes that it's either true or false. But, and it works for binary logic. Because in binary logic, there's no middle ground between true and false. That's how it's defined. But then in ternary logic, there's a new true value called unknown. So instead, we have the law of the excluded fourth, which is P or not P or unknown that P. So that is the law of the excluded fourth. Because law of the excluded middle is always false, in ternary logic, it is a tautology. The negation of the law of the excluded middle, P or not P, is now a tautology. By modal logic, or rather by our understanding of modal logic, it is intuitive that if something is a tautology, that it's, or rather if not P is a tautology, that means that it is not possible that P. If not P in all possible worlds, that means that it is impossible that P is a thing. So we can conclude that it is not possible, that the LEM is not possible. But then let's consider the case where P is unknown. Alright, let's consider the case where P is unknown. On the truth table, if P is unknown, we negate an unknown, we get an unknown. And when we do a disjunction between unknown and unknown, we get an unknown also. When we perform a possibility operator on an unknown, we get a truth. And when we negate a truth, we get a falsehood. Therefore, if P is unknown, then the tautology will be false. But there's a problem. We have arrived at a contradiction, since the tautology will now be false, which doesn't make any sense. So this is one reason for why three-valued logic is so weak. Because of the rejection of the law of the excluded middle, it leads to very weird results. When you start adding unknown truth values, you get counterintuitive results that do not fit in with what we want to use modal logic for. We invented modal logic to talk about possibilities, but then if you use this system of modal logic and you derive weird results about possibilities that are rejected by virtually everyone, then it's a failed system. There are also further objections to his system. An example is C.I. Lewis's objection that modus ponens and a lot of valid rules of inferences are invalid in Lukasiewicz logic or in the Tarski-Lukasiewicz mapping. Modus ponens can be restated or formalized in this form. If P then Q, and P is true, therefore Q. This is a statement for modus ponens. An exercise is to prove that this statement, that is to prove that modus ponens is invalid in three-valued logic. The other objection by a German logician is that Lukasiewicz logic rejects the law of the excluded middle, but modal logic accepts the law of the excluded middle. This is very similar from the previous slide, in that when you reject the law of the excluded middle, things become unintuitive, things don't make sense, and we don't want it to be like that. We want the law of the excluded middle to be a thing in modal logic. If you can't have a world in which P is false and true at the same time, you can't have a possible world, in fact P is both true and false. It doesn't model our knowledge of modal logic well, therefore we reject it. Another thing is that you can derive very counterintuitive results, as I've mentioned, as a result of the unknown. Again, this result, the proof is an exercise. I will display the answers after. For this statement, if it is possible that P and it is possible that Q, I can prove that this is equivalent to saying that it is possible that P and Q. The proofs for 1 and 3 will be shown in the next few slides. If you want to attempt them, you can pause the video and try it. Otherwise, I'll move on to the proofs. This is the proof for modus ponens, for the invalidity of modus ponens. So T/U represents Lukasiewicz / clean logic. This shows that even if you use Lukasiewicz or clean logic, when you apply the AND operator over here, you will get the same thing. Alright, you will get the same thing. In this case, when you apply Q, you will also get the same thing. Now let us move to a brief explanation of this truth table. On the right is modus ponens for binary logic. The results for modus ponens or binary logic are highlighted in purple for this truth table. The first one, the second one, the fourth one, and the fifth ones. These are exactly the same as modus ponens in two-valued logic, because P and Q are either T or F. You don't have any unknowns. The difference is when you add the unknown for the non-purple entries. You will get counterintuitive result for modus ponens. Whether modus ponens is true or false or unknown depends on this single material implication here. Alright, the true value of modus ponens adopts the true value of this second implication. If you notice, in a few cases, even if you take Lukasiewicz logic, in which this and this entries will both be true, you will still be left with one unknown entry, meaning that modus ponens is no longer a tautology. You can make everything true if you adopt Lukasiewicz logic, but with the exception of one single entry, when P is unknown and Q is false, modus ponens will actually be unknown. The thing is that because you don't know whether this is the case, it renders modus ponens not a tautology, and therefore you cannot use modus ponens as a valid rule of inference for three-valued logic. And this is very disturbing because it means that we cannot use modus ponens in modal logic if this were to model modal logic. Let's move on to the third point, to the proof of a third point. Let me explain why this statement is counterintuitive. Let's say P means that the Riemann hypothesis is true and Q means that the Riemann hypothesis is false. It is possible that the Riemann hypothesis is true and it is possible that the Riemann hypothesis is false. Using three-valued logic, this is actually equivalent to saying that it is possible that the Riemann hypothesis is both true and false at the same time. This doesn't make sense. Even if you you add a further criteria such that P cannot be the negation of Q, if you take two unrelated statements, let's say it is possible that apples are yellow and it is possible that I am in Malaysia right now. It is equivalent to saying that it is possible that both apples are yellow and I am in Malaysia right now. The problem with this is that even for weaker cases like this, it creates a link between two different propositions that is not very intuitive. It doesn't really follow. It seems more fallacious than good. It's a very non-intuitive result that we do not want to accept as an entailment of three-valued logic. In this proof, the tautology lies in the equivalent signs. We can compare this to the right-hand branch is TF, TFFF, TFT. The left-hand branch is also TF, TFFF, TFT. And because the left-hand branch and the right-hand branch are exactly the same, the equivalence will be true for all cases of P and Q. There are going to be 9 cases because ternary logic has 3 to the power of 2 different output patterns. So we have proven that this is a tautology, and we do not want to accept this as a tautology. We do not want this statement to be true for every single case of P and Q. That's it. We have completed our evaluation of three-valued logic. Because there are so many issues with it, it's very easy to denounce three-valued logic, and it's very easy to show, quite simply, why we should not adopt three-valued logic in modal logic. And as such, we continue on with our search for more elaborate, more complete, and more rigorous ways of formalizing modal logic. Up next, we are going to talk about Carnap. Carnap is a very famous guy. He's a German philosopher who moved over to America, and he's actually founded logical positivism. He is quite an atheist, quite a logical positivist, believes a lot in empirical truth, and he actually published a book called Meaning and Necessity, in which he came up with a system for modal logic. It's quite a complicated system, quite mathematical. I will explain the nature of that system, the axioms of that system, and why that system is inferior to later on Kripke's system in the next video.